Nanomaterials and nano devices, and talk, Daniel, a little bit about the challenges of integrating them with mainstream semiconductor technologies.
Yeah, I'll come back to that in a minute.
Okay.
But before I move into that, let's do a line meter, un mentimetro.
A mentimeter
Very,
right
very
now.
quickly.
Okay.
How many of you have read the Moore's paper from 1965? Raise your hand.
Oh, I.
Okay? It's only 3 pages. It's got three graphs. One of them is just a comic, okay, so we can discard it. So it's only 2 graphs, okay? One chart is the Moore's law that we all know, okay? What's the evolution of number of transistors per square inch? Okay, and start with 1, then 2, 4, okay? We know it very well. We have completely forgotten about the second chart in that paper, which is the scaling at cost. Okay? So in one chart you have the exponential Moore's law. The second chart is a parabola saying that you are reducing the cost as you increase the number of transistors per square inch. And at some point, the cost starts going up again. Okay? So you have a parabola and there is a sweet spot. And that sweet spot is when you have to change the node. Okay? And that's where you are facing a problem with the materials. Okay? So to do that, you need new technology, new materials. And we have forgotten about that. So when we talk about advanced materials, we need to put the cost of scaling or integrating that new material in the market. Okay, so when we talk about advanced material, we need to talk about scaling at cost for a niche application or for a market. And we are not doing that, right? Because we have forgotten about the second chart. So Moore's law, it's been a lot of many years that we are not fulfilling it. We are only fulfilling half of the Moore's law, but we are not scaling that cost anymore. Every year when we reduce the node, the cost of producing a chip is going up, okay? So this is the first message. Second message, when it comes to material science, there's another lesson from the past that we have forgotten. I used to be a grower. I did my PhD doing growing 3-5s in a solid source molecular beam epitaxy, handmade, okay? Very old machine, very unique. So my background in 3-5s is very strong. And I remember when I started my PhD back in 2001, the big announcement was Motorola. Okay, Motorola was leading the way on RF communications with gallium arsenide. And they announced, we can do gallium arsenide on top of silicon in the lab. This was 2001. In 2004, Motorola announced, we cannot scale it up. We failed. We found a lot of barriers, okay? And they throw the barriers to the community. This is what we've learned. These are the barriers to scale up and to be able to grow gallium arsenide on top of silicon, okay? And now, Philippe has mentioned it in his presentation. In 2024, we have used nanotechnology, nano ridges on silicon to be able to grow very pristine gallium arsenide directly on silicon with very unique and good mobility, good properties, no dislocations, no defects. It's taken us 25 years, right? And this was thanks to Motorola making it public that there are these barriers to scale at a cost, okay? We need to put this into the equation. We are talking about 2-dimensional materials, for example, graphene, transistor metal dichalcogenides, trichalcogenides, quaternary alloys. But we are not thinking, with scientists, we are not thinking at scaling it at cost. And the reason why is because science, at least in Europe, science is designed for success. But science is all about failure. So when you're a scientist and you want to find the barriers to scale, it's very hard to obtain funding. If you tell your funding bodies, look, I'm going to fail in my research, they are not going to fund you. So it's very hard to find the barriers to scale the materials, right? Because scientists are obsessed with the new properties, the quantum properties, all the nice emerging things of quantum materials, and win the Nobel Prize because I've discovered this new law of nature, right? And what we need is technologists. We need people being paid to find the barriers, talk to the academics, say, look, these are the barriers, now you do the science, and now we go back into the lab and we try to scale it up. And the sooner we scale it up, the sooner we are going to find the barriers, the sooner we can talk to the scientists, and we keep doing this again and again and again, so we progress faster. This has not happened with two-dimensional materials, okay? So last year in 2024, there was a big paper in Nature from Samsung talking about scaling up and producing molybdenum disulfide in a 200 millimeter wafer. Mobility was 21 volts per centimeter squared per second. So mobility in silicon is 1,400, right? It's very hard to scale these materials at cost for a specific market. So we need more technologies working on that approach. We need to put funding on finding the barriers and then going back to the science.
Okay. So the nano, I guess we go back to my first question a bit more, my nanomaterials question.
The nano. So we need to look at nano, not only as nanomaterials because of the emerging properties that are there, and I'm pretty sure that they are in the roadmaps. We will exploit those super nice properties, like graphene has a super high mobility, right? There's no other material in nature that has the mobility that graphene has, right? So this is probably very useful for ultra-fast communications in wafer. But nanoscience and nanotechnology is also a toolkit. You see, I mean, you are capable of growing gallium arsenide on silicon because you are able to produce these nano ridges on a silicon wafer. So we need to look also at nanoscience as a toolkit, enabling us to do things that we cannot do. The other thing that I think is going to come in a nanotechnology world is advanced accelerated discovery because of the AI. So there are materials that they don't exist in nature. For example, the silicon we use for the semiconductor industry is the most unique material in the universe. There are no other materials in the universe with the degree of purity and perfection that we are producing in the semiconductor industry. Those other materials will come. This will happen in materials that we cannot imagine. I think that we will see the emergence of more ternary alloys, okay? Not only transition metal dichalcogenides, but trichalcogenides, so mixing a metal with two other atoms.
These are these high entropy materials now, which are also another possibility.